what 3.2 is. So 3.2. 3.2 is 4 ways that a function can fail to be differentiable. And what that means is the derivative does not exist. So we're talking about 4 ways that a function can fail to be differentiable. And this is a new word here, differentiable, I think. So from year to year, I forget when I've mentioned it, when I haven't. So I think differentiable is a new word this year. Differentiable means that it does have a derivative. So if it fails to be differentiable, that means the derivative doesn't exist. Okay. So differentiable derivative does exist. Fails to be differentiable means the derivative doesn't exist. So what we're talking about is 4 ways this can happen. Okay, we've already had one way that this can happen, but I've kind of mentioned it briefly, so I'm not sure if you know, but do you know one way that a function can fail to be differentiable? Yeah. Yeah, it's called a corner point. So remember yesterday when we had that graph that looked like an upside down V, and at the top the slope was changing dramatically? That's called a corner point, and at a corner point, the function is not differentiable. And that happened the day before as well with the piecewise graph. Okay, so number 1 is if there is a corner point. And the official way of testing whether there's a corner point or not is you take the limit as x goes to a of f of x minus f of a all over x minus a. So, of course, this is how you figure out whether the derivative exists or not, right? Because this is the formula for the derivative. And what happens with a corner point is you do the left-hand derivative, and then you also do the right-hand derivative. And with a corner point, you get a number answer here, and you get a number answer here, but those numbers are not equal. So for example, maybe you'd do this limit, and you would get 5, and you would do this limit, and you would get 3. And so then overall, the limit doesn't exist. So that's why the derivative doesn't exist, but these are not equal. Okay, so this needs to be a number, and this needs to be a number. I'm waiting for hashtag to not mean number. Does it still mean number to you guys? A little bit. Have you seen that or not? Yeah, one of these years people won't know that. But anyway, to me a hashtag stands for number. That was way back in the day before there was hashtag for anything else. So. Okay, so this is going to come out to a number. This is going to come out to a number. And they're not going to be equal. And when that happens, you know there's a corner point. And then, of course, when you look at the graph, it's easy to spot a corner point. But that's the kind of the not official way. This is the official way to figure out whether there's a corner point or not. Okay, so flip back to 3.1b. And part A of example 1, do you see we calculated the limit towards 2 from the right side? And we got 3. And then we took the limit from the left side, and we got 5. So that's a corner point. at 2, there's a corner point there. So we got a number for this, we got a number for this, and those numbers are not equal. So that means overall the derivative is not equal. Yeah, sure. And so that means it's not differentiable. Okay, so that's a corner point. All right, the next kind of non-differentiable place is called a cusp. Okay, and a cusp is, you know, when you were in grade school and you drew pictures and you put birds in the sky, but the birds looked like this because you were a really good artist and you just did birds like that. That's what a cusp looks like. Or it could be upside down, which would be a crashing bird, I guess. So those are what a cusp looks like. Hey. Thanks. Abby, that's for you. Okay, so that's what a cusp looks like. But we need the official way of figuring out whether there's a cusp. So what happens is when you take the limit of f of x minus f of a all over x minus a, when you go from the left side, you get positive infinity. And when you come from the right side, you get negative infinity. So since you're getting different things from different sides, that means overall the limit doesn't exist. The limit without the direction on it doesn't exist, which is why the derivative doesn't exist, because that limit is the derivative, right? And so that's why there's a non-differentiable point. But it's a particular way of not being differentiable, where you're getting infinity on one side and negative infinity on the other side. So you're not getting numbers like with a corner point. When you take these limits, you get actual numbers, whereas with a cusp, you get infinities. And these could be swapped. So the top one could be negative infinity, and the bottom one could be infinity. The point is you're just getting two different infinities when you take the limit. Okay, so that's a cusp. So now you can see a cusp on a graph. It's going to look like that. And then you can officially, without a calculator, see where there's a cusp with these limits. Okay, the next one is called a vertical tangent. And a vertical tangent looks like this. And the point in question is right there. So what's happening with the vertical tangent is it's so crazy steep there that it's basically for one moment straight up and down. And so that's why it's not differentiable, because it doesn't have a slope, because that slope is undefined. Okay, so the official way to find out where there's a vertical tangent is to take the limit as x goes to a of f of x minus f of a all over x minus a. And that limit is going to come out to either positive or negative infinity from both directions. So you're going to calculate both of these limits, but they're going to come out the same. They're either both going to be infinity, or they're both going to be negative infinity. And that's then called a vertical tangent. So you're still getting infinities, but they're not different infinities. They're the same ones from both ends. Okay, now this word vertical has popped up before, so it's good to connect. When have we talked about vertical other times in this class? A vertical asymptote, right? Okay, so how do you find a vertical asymptote? Yeah. So that's the first thing I want to point out. When you're looking for a vertical tangent, you take the limit as x approaches a number of just plain f of x, right? When you're doing a vertical tangent, you're taking the limit of just f of x. When you're taking the derivative, you take the limit of this mess, f of x minus f of a all over x minus a. Okay, so for looking for a vertical tangent, you're calculating this limit, whereas with a vertical asymptote, you're calculating that limit. They're different limits. The problem is we do this limit so much that people forget that this one is different, so that's why I wanted to mention it. Yeah?
With the vertical tangent, though, if you just take the limit of f of x, it should come out to that point, not infinity, correct?
Yeah. So there wouldn't be a vertical asymptote there, because for it to be a vertical asymptote, this limit needs to come out to infinity. Good. So that's the next thing, to see if it's a vertical tangent. This limit would be coming out to infinity, rather than that limit coming out to infinity. Oh, and how do you know what a is? Like, you've got to know a number to test, right? So if you're looking for a vertical tangent, what number do you try? Yeah. What makes the function undefined, which is often what makes the denominator 0, right? Okay, so that's a review of vertical asymptote, but that's not the topic for today. But since the word vertical popped up, I wanted to contrast those. Okay, so that's a vertical tangent. You take the limit of the slopes and you get positive or negative infinity. Okay, then the last type of discontinuity, or not differentiable place, is if there's a discontinuity. So what I'm saying is, anytime a function is not continuous, then it's automatically not differentiable. In other words, anytime there's a place where there's a jump in the graph, there's not going to be a slope there either. So the derivative not existing means that there's not a slope, right? So there's not a slope here because it's straight up and down. There's not a slope here because it's pointy. There's not a slope here because it's pointy. Okay, but whenever it's not continuous, there's also not a slope. So that means that not continuous automatically leads to it not being differentiable. Okay, so now that we've got our information, that's not a few problems there. Now we're going to have f of x equals x to the 1/3 power. And we need to show that f is not differentiable at x equals 0, and then categorize. F of x equals x to the 1/3 power. Show that f is not differentiable at 0, and then categorize that. For you in future classes, this is Star Wars Day during homecoming week. Okay, that's enough of that. Maybe I'll use this to point at this. I stole that from my 5-year-old. If he knows I have that mask, he'd be very upset with me. He would not. I didn't ask him because I knew he'd say no if I asked if I could take it to school. a little guilty, but not too guilty. Okay, so if we're going to see if this is differentiable, that means we're trying to figure out if the derivative exists, right? To show that it's not differentiable, I have to show that the derivative doesn't exist. To show that the derivative doesn't exist, I have to calculate the derivative. And to calculate the derivative, I have to do that big nasty limit. Okay, so it's the limit as x approaches a, but in this case, they're telling me a is 0, right? So it's the limit as x approaches a of f of x minus f of 0 all over x minus 0. Okay, so I just start plugging in. F of x is x to the 1/3 power. So I'm going to take the limit as x goes to 0 of x to the 1/3. And then f of 0 means 0 to the 1/3. Well, the 1/3 power means the cube root. So I'm just taking the cube root of 0. So that's 0. And then on the bottom we have x minus 0. So these zeros are kind of silly, right? I don't really need to write them. So I guess I'll put another step. Limit as x goes to 0 of x to the 1/3. And this is x to the 1st power in the denominator, right? And so then what do I do with these exponents? Subtract them, right? Whenever you divide, the shortcut is to subtract exponents. So take 1/3 minus 1. So that gives me the negative 2/3 power. And so I'd prefer to write that as 1 over x squared. It's in the denominator because it's negative, right? So it's the positive 2/3 power in the denominator. And then the 2/3 power means square the x, and then later cube root. So it's in the denominator because of the negative. It's squared because of the 2, and it's cube rooted because of the 3. There's a lot going on there, but those are the 3 reasons: the negative, the 2, and the 3. Okay, so now I'm just going to kind of think about this limit in my head. If you plug in like 0.1, 0.1 squared is going to be still pretty small. And then the cube root of that small number is still going to be pretty small. So you're basically taking 1 divided by a small number. And so like 1 divided by 0.01. That gets big. 1 divided by 0.01 is 100. Because 100 0.01s fit in 1. Okay, so as this number gets really small down here, the division is going to get really big towards infinity. Same thing with a negative number, because when you take a negative number and square it, it's going to end up being positive as well. So this is going to positive infinity. Now, if you didn't follow that logic, you could always make a table for that, right? Off to the side, just put in 0.1, 0.01, and you'd see that it's going to infinity. Okay, so we took this limit and we got infinity. So that means that this, which is the derivative at 0, right? This is called the derivative at 0. We got infinity, which means that this limit doesn't exist. I mean, it equals infinity, but infinity doesn't exist, so the limit doesn't exist. So since this limit doesn't exist, this is called the derivative. That means the derivative doesn't exist. So that means it's not differentiable. So we just proved that the function is not differentiable at 0. So, and it said, show that it's not differentiable at 0. So we just took care of the first sentence. Show that the derivative doesn't exist, aka show that it's not differentiable. Okay, and then they want us to categorize, so that means we need to put it into one of those 4 categories over there. So which one is it falling into? Yeah, it's a vertical tangent, because the limit came out to infinity. And it also would have been a vertical tangent if the limit had come out to negative infinity. Okay, so this is a vertical tangent. Or I guess to say more precisely, there is a vertical tangent at x equals 0. So notice we did all, oh yeah, sorry, Austin, go ahead.
I was just gonna ask, why didn't we split it up into like two
I did, kind of, because I plugged in negative 0.1 and positive 0.1. But the negative and the positive doesn't matter because the squaring is going to give you the same answer either way. So that's why I didn't need to split it up, because when I did it in my head, it was coming out the same. Yes? Well, whenever you're taking a limit, you always have to come from both ends. It's just, in this one, I didn't bother writing down that I was coming from both ends because in my head, I knew the negative squared was going to come out positive. So it's just a matter of how complicated the limit is, I guess. So if you're having trouble figuring it out, then one thing to do is to split it up into the separate ones. And then it might break it down easier for you. But whenever you do a limit, you're doing both sides. Good. All right, is everybody okay with that then? Thanks for asking questions, it really helps. Colin might have a question.
I don't see why it's not a cusp.
Because in order for it to be a cusp, the limit from the left would need to be negative infinity, and the limit from the right would need to be positive infinity, or vice versa. You would. Right, exactly. If the infinities match up, then it's a vertical tangent. Whereas if you get two different infinities, then it's a cusp. Good. All right, so let me show you one. Let me show you another one. So this is f of x equals the absolute value of x to the 1/3 power. And same directions show that f is not differentiable at x equals 0 and categorize. I gotta make sure I use my props because it's more fun, and also, I'm acting for the camera, so hopefully, Team TV, you'll see my videos on calculus and recruit me for their other videos. I know I look really awkward on camera, so I know there's no chance of that happening. Okay, so how am I going to show that it's not differentiable at 0? Take the limit of the slopes, right? Calculate the derivative. Yes, good. So take the limit as x goes to 0 of f of x minus f of 0 all over x minus 0. If I was trying to show that it wasn't differentiable at 1, then I would put 1s in these places, right? But they said show it's not differentiable at 0, so that's why I'm putting 0 in these places. I'm calculating the derivative at 0. Okay, so this time, the f of x is the absolute value of x to the 1/3. And then if I plug 0 into that, the absolute value of 0 would be 0. And the cube root of 0 is 0. So that's minus 0. And then it's also x minus 0 in the denominator. Okay, so those are unnecessary, right? So I can just kind of get rid of those. Okay, now this time, since it's absolute value, the positive and the negative are going to behave differently. So I am going to split it up into the two limits. So this one, I guess this one's a harder limit, and so I'm going to go ahead and split them up. Not just in my head, but actually on paper. Okay, so I'm going to take the limit from the right side and the limit from the left side. So limit from the right side of the absolute value of x to the 1/3 power all over x, and also the limit from the left side of the absolute value of x to the 1/3 power all over x. Okay, so when x is positive, what do the absolute value signs do? Let me say that again. When x is positive, what does an absolute value do to a positive number? Nothing, right? It just spits back 3 if you put in 3. So when I'm picking numbers that are positive, that are bigger than 0, these absolute value signs are totally unnecessary. So then I do my same subtraction that I did on the last problem, right? 1/3 minus 1 is negative 2/3. So this is 1 over x to the 2/3. And we already established that this is going to go to infinity. So just let me talk that through again. 0.1 squared is a small number. The cube root of that is still a small number. And so we're taking 1 divided by a really small number, which gets really big. So that's going to infinity. Okay, now over here, what does absolute value do to a negative number? It makes it positive, right? Okay, so what's another way to take a negative number and make it positive? Multiply it by -1, right? So if I take the absolute value of -3, that gives me 3. Or if I multiply -3 by -1, that gives me 3. So if you have a negative number, absolute value behaves exactly as multiplying by -1. So I can get rid of the absolute value signs as long as I multiply the number by -1. Okay, and then this distributes, right? So -1 to the 1/3 is -1. And then x to the 1/3 divided by x to the first is x to the -2/3. So then if I pick a really small negative number and square it, it's going to be a positive small number. The cube root of that is a positive small number. If I take -1 divided by something like 0.01, that gives me -100. So this is going to a negative big number. And so that means that we're getting different infinities. So that means there's a vertical tangent at x equals 0. Sorry, I said it wrong. There is a cusp at x equals 0. You guys are like freaking out, like, oh my goodness, I thought I knew something. For one moment, I thought I knew something, and he shattered my... No, you were right. It's a cusp. Okay, just want to make sure you have in your notes that if a function's not continuous, that means it's automatically not differentiable. But the other way is not true, right? If it's not differentiable, it still could be continuous, right? How? it could be a vertical tangent or a cusp or a corner, right? So there are three scenarios where you could be continuous yet not differentiable. But the other way, if you're not continuous, you're automatically not differentiable. So you don't even need to check. If you know it's not continuous, just automatically it's not differentiable. Yeah. Even if it's removable, that's right, because removable means we could create some other function that would be continuous. But this function is not continuous, and so it's not differentiable. Maybe that other one would be differentiable, but good. Great question.